Okay, welcome everybody. So let's continue exploring bases for vector spaces and the coordinates that we get when we pick a basis for our vector space. So let's consider a vector space V, which in this case is R2, and I'm going to pick a basis B whose first vector is 1, minus 2, and the second vector is minus 3, 4. And these two vectors are linearly independent, and between these two vectors, we span all of R2. So they form a basis. And let's pick some vector x in R2, and we know that its b coordinates are 2 minus 6. Okay, so this means vector x is not 2 units to the right and 6 units down. This tells us vector x is 2 units in the direction of 1 minus 2, and then minus 6 units in the direction of minus 3, 4. So we actually wind up at some other point in R2. And so the question that we want to answer here is, well, how can we figure out where we actually wind up in R2 in terms of this standard basis? So if I wanted to take this set of instructions and give somebody a much easier set of instructions that just says go this many units to the left or right, and then go this many units up or down, and you'll wind up at the same destination as going 2 units in this direction and minus 6 units in that direction. And the way that we move between these bases is by matrix multiplication. So what this b coordinates are telling us is that, right, we're going 2 times 1 minus 2 minus 6 times minus 3, 4. And doing this arithmetic is equivalent to taking the matrix over here, whose first column is 1 minus 2 is the first column vector, and whose second column, minus 3, 4, is the second column vector in our basis. So we're going to take this matrix, whose columns consist of each basis vector in B, and we're going to multiply this matrix, and the vector in B coordinates that we have of 2 minus 6, and that gives us 20 minus 28. So this is the coordinates of our terminal point with respect to the standard basis. So this means we're 20 units to the right and then go 28 units down. So this matrix that we just defined, P, whose columns were each one of the vectors in our basis, we call the change of coordinates matrix from this basis B to the standard basis in R2. And we can generalize this to higher dimensional spaces. So if we take B to be a collection of n different vectors, column vectors that form a basis for Rn, then we can define the change of coordinates matrix from any basis B for Rn to the standard basis for Rn by constructing this matrix P, again, whose first column is the first basis vector, second column is the second basis vector, all the way out to its last column is the last basis vector in our set B. So we denote this matrix, typically gets denoted with a P, and we put a subscript with indicating what basis this is referring to. And so this is going to map coordinates from B, this kind of non-standard basis B, into the standard basis for Rn. So right now we're just working with a change of coordinates from one vector space back into itself. We can use this change of basis matrix that we just defined to go in the other direction. So the way that we just defined that change of basis matrix was to go from coordinates in some non-standard basis B back into the standard basis for, in this case, R2. Let's say we still have this same basis B, whose first vector is the column vector 1 minus 2, and the second vector in this basis is the column vector minus 3, 4. And we're working with the vector space R2. And so here's the vector x in R2, the column vector 8 minus 11 in usual coordinates. So here we are located 8 units to the right and 11 units down. But let's say I want to describe this point, this vector, not in terms of standard basis elements, but in terms of this basis B. So we want to find the b coordinates of x. So let's see how this would work. We know we have a change of basis matrix P 1, minus 2, minus 3, 4, but this is what we would use to map from b coordinates to the standard coordinates using the standard basis. This question is asking us to do the reverse. We want to take standard basis elements, coordinates here, and be able to write this same point in terms of coordinates relative to this other basis b. So we want to do the inverse of this process. So that means we go ahead and find the inverse of the change of basis matrix. So we're going to find P inverse. And in this case, again, the change of basis matrix would be to go from B into the regular standard basis would be this matrix P, whose first column is 1, minus 2, whose second column is 3, minus 4. We want to go the other way, so we can find the inverse of this matrix. And for the case of a 2 by 2 matrix, it's not too hard to find the inverse, right? We can find the determinant of this matrix, which would be 4 minus 6. So the determinant here is minus 2. And then we interchange the diagonal entries and change the sign of the off-diagonal entries and divide everything by the determinant. And that gives us P inverse. So in any case, you could also use Python to track down this inverse matrix. But once I'm found the inverse of the change of basis matrix, then we are going to go ahead and say we are going to apply P inverse. I left off a really important minus sign here. This is the inverse of P to the coordinates in our standard basis. And when I multiply by the inverse of P times our standard coordinates, what we get is a column vector that is telling us the B coordinates of that same vector. So this is telling me I should go half a unit in this direction and then minus 2.5 units in this direction in order to wind up at 8 minus 11.